slow down or stop me and ask questions if you want to learn more about what's going on with Tephra. Okay, so I'm going to share my screen, I think. And so what you should do, if you can, is launch a Jupyter notebook and in Victor and follow along if possible. And so we're going to develop this much the way we did last time. I'm going to share the entire screen just to make it a little bit easier. Whoops, sorry. And have you guys seen this video? We were talking about Iceland last time. I just wanted to bring this up. Here's the curtain of fire in the background, up in the upper left-hand corner of the picture. And here's lava flow, I guess, from a couple of weeks ago. You can see the rate at which that lava flow is advancing is pretty spectacular, and how it's basically vaporizing the road as it flows across it and goes off into the distance. So Iceland's going to continue to be interesting for quite some time, and in a couple of weeks, I guess, maybe next week, I'm not sure, we're going to be talking about lava flow modeling, or and Sam are going to be talking about lava flow modeling. So stay tuned for that. It's pretty interesting and super relevant at this point. So this is this is a video somebody sent around in our group from a magazine I've never heard of. I'll put it in the chat for you to actually download that link if you're interested. It's pretty amazing video. Very interesting article about volcanologists monitoring the eruption sort of from a human interest perspective. Okay, so last time we were talking about estimating a fusion rate at a vent given a fire fountain. And remember, the basic strategy that I developed was to derive an equation for explaining how we might use the fusion rate to model the eruption. And we decided, based on the sort of units, looking at a quick dimensional analysis of the problem, that we could calculate a velocity at the vent of the magma gas mixture as it came out, and use that to estimate an effusion rate if we knew something about the ratio of the density of magma to the density of the entire gas pyroclastic mixture coming out of the ground. And we referred to some literature to do that. Then we developed some equations and solved the problem. So a key thing about this was to look at uncertainty and the propagation of uncertainty through the problem. And so we did that with some simple Python tools, mostly from NumPy, where we looked at the fissure length as a random normal distribution. We looked at the fountain height as a log normal distribution, acknowledging that there's aleatoric uncertainty in the fountain height. That is, there is random variation in the fountain along the length of the fissure that we can observe directly. And of course, there's measurement error in determining the fountain height as well. So that's more of a full aleatoric uncertainty. And then we had uncertainty in the aperture diameter, and we could propagate that through the equation to ultimately get uncertainty in the effusion rate in cubic meters per second. So I posted that notebook in Box, not this notebook exactly, but a more detailed notebook in Box, in the Box folder, which you can check out. And then remember, I also went into the gas dispersion problem and looking at how gas disperses from the volcanic eruption and what gas concentrations might be downrange of the erupting volcano, mostly in terms of sulfur dioxide flux, but you could do that in terms of other gas species as well. And that was using an analytical solution to the advection diffusion equation. So there's method to our madness. Today we're going to actually continue that and talk about the advection diffusion equation now in terms of distribution of pyroclasts or tephra fallout from volcanic eruptions. And there's a bunch of code out there. There's a bunch of code on Victor for looking at Tephra dispersion. One model is called Tephra 2, which colleagues and I developed a few years ago. And there are a number of other codes online specific on Victor, like Puff and High Split. And we're going to be talking about those a little bit today. But mostly I want to look at this problem from an analytical perspective and really give you a leg up on understanding Tephra dispersion in terms of the math people use in order to solve this problem. And we're going to understand that math not from the perspective of a mathematician necessarily, but from the perspective of a volcanology problem. Okay, so I'm gonna go ahead and start a notebook. So as usual on Victor, I'm starting with a blank space. And for me, what I usually do is start with some markdown. And so this notebook is going to be about let's just call it a simple Tephra dispersion model that we're going to explore, and we're going to use an analytical solution to the Tephra dispersion. Just like with gas dispersion, there's also numerical solutions which we can implement, and it really depends on the nature of your problem to decide whether you're going to use an analytical solution or a numerical solution. So in general, in volcanology right now, if people are interested in problems like, well, what's the concentration of Tephra particles in the atmosphere, sort of an aviation safety problem or something like that, then they tend to use a numerical solution. If you're interested in modeling how much Tephra accumulates on the ground at a given location, then people have found analytical solutions are pretty good for that. Okay, so let me give you a little bit of historical background. There's sort of three papers I want to go through about this. One is by this guy Suzuki in 1983, and this is oops, I'm sort of halfway through the paper at this point. This is a paper that was published in a pretty influential book about 40 years ago called Arc Volcanism. It was edited by Shimozuru and Ito Yokoyama. And it summarized a lot of active research in volcanology in Japan at the time. And one of the papers was a theoretical model for dispersion of Tephra by Suzuki. And so this is a very influential paper. It basically sparked a lot of research into how do we classify volcanic eruptions? How do we characterize their volume? How do we, using words we use today, magnitude and intensity of the volcanic eruption? You can see that Suzuki was interested in classifying the bigness of the eruption using some nomenclature from George Walker. So you might know that George Walker, a very famous volcanologist working mostly in the 70s and 80s, but all the way up into around 2000. Walker took a sedimentological approach to understanding volcanoes and pyroclasts associated with volcanoes. And so he started classifying eruptions in terms of the fragmentation of the eruption, the area covered by the Tephra blanket, and so on. And Suzuki basically came up with the idea that he could use the advection diffusion equation to get a different angle on that kind of problem. And so we're not going to read through this paper or anything like that, but I just want to point out a few ideas here. One is Suzuki developed a very early model, a flow chart, essentially showing what are all the important things that happen during Tephra dispersion in the atmosphere. And a lot of this is pretty close to what we think of today and how we model things today. Not quite, but he did a great job of summarizing that. And then another thing he did is he realized that he could apply the 2D advection diffusion equation. Sometimes it's called the convection advection equation, but we don't need to worry about that nomenclature. It's this partial differential equation to explain the concentration of Tephra as a function of time and distance away from the volcano. And so the nice thing about this is Suzuki didn't have to do a lot of basic research on this equation. It already existed because it's been applied to a ton of problems, everything from pollution, dispersion in the atmosphere to groundwater contamination to other kinds of natural diffusion or advection diffusion processes that happen globally. So it's a well understood equation, both in the atmospheric sciences and in the physical sciences for characterizing diffusion and advection as things go along. And we don't want to necessarily get into this equation in too much detail here today. I can if you want me to, but basically if we've got this variable in the numerator here, say it's a concentration as a function of time, we can characterize that in terms of the advection term, that is the change in concentration with distance, x, and that's multiplied by u, and u in this case is a velocity term. And we've also got diffusion of material. So as the material is blown downwind, say from a Tephra column, it also spreads out in the atmosphere, diffuses in the atmosphere, and he's got it diffusing in the x and y directions. And so x in this case is the concentration downwind, that is in the direction that the wind's blowing. So that wind velocity is only part of this term, this advection term up here up front. And there, y is defined as the crosswind distance. That is, how is Tephra spreading out as it goes downwind in a crosswind direction. Okay, and so he developed an analytical solution to this. I just want to get down to that analytical solution. He says in equation 2 here that he can characterize the concentration now on the ground, integrated over time in terms of a amplitude term, essentially, which has to do with the amount of material released and how it diffuses in the atmosphere down here in the denominator, times this sort of exponential decay function. And so this is a Gaussian approximation to the advection diffusion equation. Basically what we're saying is that diffusion is a process like random error, like I was talking about last week, where material sort of begins to spread out and cover increasingly large areas away from the plume center line as it flows downstream from the Tephra plume emitted by the volcano. So it's a very elegant way to think about it. And in fact, the advection diffusion equation goes back to people like Gauss and others who were interested in these sorts of diffusion problems, characterizing diffusion in terms of random error. In fact, one of the reasons Gauss is basically considered to be a genius is that he was able to relate this random process of diffusion to the random process of error, and he conceptualized those things as being sort of similar. Okay, so basically then we're talking about developing an analytical solution to this equation. I'm gonna get into that again in a minute. I just want to point out that the Suzuki had all kinds of problems he had to overcome, like what is the scale of diffusion? And he used some examples from volcanic eruptions, basically the shapes of isopac maps, the actual dispersion of Tephra to sort of understand and quantify what the diffusion is associated with these eruptions. And he called that an apparent diffusion because and for reasons I'll get into in a second, but he referred to that as an apparent diffusion because it's not only the physical diffusion of Tephra in the atmosphere by atmospheric processes. Okay, he also had to develop an equation for the rate at which particles fall out of the atmosphere. And so he developed this sort of complicated looking, probably overcomplicated formula for characterizing the settling velocities of particles in the atmosphere. and used data for that had been collected by George Walker and by Lionel Wilson and colleagues in the 70s, showing what the relationship is, excuse me, between the terminal velocity of particles as a function of the mean particle diameter, and tossing density in for good measure, and something called the shape factor. Essentially, the shape of the particle influences the settling velocity in the atmosphere. And so you can see that there's some sort of general relationship, and Suzuki came up with this rather complicated, rather cumbersome equation to describe what that relationship might be. But basically, we have to know how long it takes for particles to settle out of the atmosphere. And so that was his attempt. And he had some really other nice things to say about where particles might be released inside the eruption column and things like that. But we can go back to that with some updates before we do it. And anyway, the output of this, if I can scroll down, was forecasts of what the isomass or isopack thickness might look like as a function of distance from the volcano. And he wound up heavily parameterizing this problem. But in my opinion, it was one of the earliest, best efforts to actually develop a Tephra model and to use it to understand a volcanic eruption. He applied this to the Mount St. Helens eruption. He made a few errors because he didn't understand all the processes, like there's a secondary maximum in the Mount St. Helens deposit that's related to the aggregation of ash. As we now know, Suzuki didn't know about aggregation of ash in 1983, so he missed that process. But you know, geez, he did a great job of trying to sort this out. And one of the most interesting things to me about Suzuki is he was working on this as a PhD student, and he was working with another volcanologist, his professor, and his professor, Tadi Wee, got kind of, the story is Tadi Wee got kind of mad at him for spending so much time on this crazy model of Tephra dispersion, and he wanted him to go out and do more volcanology instead and characterize debris avalanche deposits, which were the rage in 1983 because of the eruption of Mount St. Helens. And so he got in a bit of trouble for writing this paper and spending too much time on it. And it turns out to be a wonderful contribution to the literature. So, you know, don't always listen to your professor when they say what you should be doing. Try something else. Okay, so that was the state in 83, and I'm going to skip ahead to another paper. This is by Costanza Bonadonna and a bunch of other jokers working on these Tephra models to try to characterize volcanic eruptions, and it's with this application to Tarawera in New Zealand. And so basically, if we go down, one thing I want you to see in this paper is it turns out there's a lot more volcanology in this paper, right? So things have been learned about the dispersion of Tephra as a volcanological process, and the advection diffusion equation is the same essentially as Suzuki implemented way back in '83, but it adds a little more sophistication because we have a better understanding of the volcanology when this is developed. So here is in equation 5 here. Here's the same advection diffusion equation. That's a sort of more simplified view of it than Suzuki presented. But basically, we're saying that there's diffusion of particles, or the mass loading of Tephra at some point, X and Y, is going to be a function of where you are. In terms of X and Y, the advection of particles downrange, and this term sigma, and sigma here is related to the time it takes for particles to fall out of the atmosphere from their release height, the diffusivity in the atmosphere, and related factors. So the paper then goes into sort of describing what these different parameters mean in terms of atmospheric and volcanological processes. And the net result is trying to forecast something about where particles wind up in what volume. And ultimately, Costanza used this to develop both maps of past eruptions and hazard curves, somewhere down here. There are hazard curves for how much tephra might accumulate in a given spot given an eruption of the volcano. So again, looking at the aleatoric uncertainty in the eruptions, since we don't know the masses of future eruptions, we don't know the particle size distribution and so on, we need to look at that uncertainty very carefully. And so this paper represents an early version essentially of Tephra 2, which we continue to work on for a number of years and refine. And it's the same model that is on Victor and is used today. And then I wanted to talk about one more paper really briefly. I hope I'm not losing you too badly here. Here's a paper by Ling Lim. She was a doctoral student at Massey University, and she was in mathematics. So she took a very different view of Tephra and Tephra dispersion models. She looked at it from a mathematical perspective. And some of what she did was very, very elegant in terms of recasting the equation in terms of parameters that we can implement in a Jupyter notebook, for example. Her main point in this paper, which was her dissertation, was looking at different source shapes. Like, do we have a long curtain of fire, or do we have a umbrella cloud, or do we have a bent over plume or something like that? Looking at those different different source shapes and their impact on isomass maps. But I think the elegant thing about this is she was able to look at the mathematical basis for the eruption in a lot more detail, in a different way, I should say, than we had previously. And so she started with this same advection diffusion equation. And so basically these terms for C that are not squared are advection terms. So the change in concentration with time depends again on the velocity in the downrange direction. She introduced this term S, which is the settling velocity, which is the rate at which particles fall out of the atmosphere, and these diffusion terms. So it's essentially the same approach that Suzuki used, the same approach that Costanza used, and so on. And what she did is she tried to come up with an analytical solution for this expression, keeping it as general as possible. And so this is kind of a cool development here where she says, well, what is the concentration as a function in space, x, y, z, and t? And so that depends on this train wreck on the right-hand side of the equation, and that train wreck goes on and on and on. Okay, so if you want an analytical solution to the problem in its most general form, Ling gave it to you, but it's a pretty complicated looking equation. So she went through, the rest of this paper kind of goes through and simplifies it, and I want to concentrate today on equation 3. And so let's look at that. This is the concentration on the ground. So Z is 0. We're on the ground now. Is a function of x and y. And it depends on S, that's that settling velocity term, Q, which is the amount of mass we release into the atmosphere, H being the height of the release point in the atmosphere, so where in the column that tephra is released from as it flies into the sky above the volcanic vent. Dx and dy are these diffusivity terms. This is that same exponential term that I showed you in Suzuki's paper and showed you in Costanza's paper, and we'll unpack that in a minute. So what I want to do is actually start a notebook with this equation and work through it. And in the process of working through it, I'm hoping some details of Tephra dispersion are revealed to you and become more easily understood than would be if we just sort of jumped into, say, using Tephra 2 or using a different Tephra dispersion code. Okay, so let's do that. I'm going to go back to the notebook, and I said Suzuki 83 and Bonadonna 2005, and Lim, I guess it was 2008. Those are those papers I'm basing this on here. And let's just look at the form of the equation from Lim 2008. So I've got this equation up here, and I'm going to just sort of go through how I would build out this equation using LaTeX in my Markdown, so you can better understand how to do that. And then we'll talk about these things in a minute. So we're solving for f of x, y. That's on the left-hand side of the equation. That's the mass loading or volume loading of Tephra at a point x, y due to the volcanic eruption. And the first thing in Lingling's equation is this sort of amplitude term. And that amplitude term was related to the settling velocity. I'll just call it S in this equation. And the amount of mass released into the atmosphere, my source term. And then the denominator was 4 pi, and then the square root of, the square root of dx and dy. So let's just run that, see what we got. Okay, so there's sort of the first part of the equation, which is governing essentially the amplitude of this term. And I forgot h, I see. Okay, so h is in the denominator as well, 4 pi h. Okay, and so let's define the variables before we get too out of hand here. So s is the settling velocity of particles, Tephra particles, pyroclasts if you want. Q is the mass in the atmosphere. That's the amount released in the column itself, the amount of Tephra. H is the release height. Made it a capital H for some reason. That's where the particle is in the plume when it's released. And then dx and dy are going to be our diffusivity terms in the crosswind and downwind direction, right? Sort of how much it spreads out as a function of time. And let's say y crosswind, and let's say x is downwind. That just simplifies the geometry of the calculation a little bit if I specify it in those terms. I didn't. It's easier if I put spaces here, little extra returns. It makes a new paragraph and it kind of is easier to read. There we go. Okay, so those are those terms. So let's take a look at this. What's going on with Tephra dispersion in terms of this amplitude term? Well, we might want to think about it in terms of units. And so let me just add units to this. I'm going to rewrite that expression in terms of units. So I'm going to say f of xy is going to be equal to, and then so the units of s are meters per second, right? That's the settling velocity of the particle in meters per second times q. And so q is this mass loading term. That's how much Tephra is actually released by the volcano. And very often we think about that in terms of kilograms. So the total mass released by the volcano. You can also, as I'll get into in a second, you can also think about that in terms of volume if you want to. Okay, and then we got this term over here in the denominator. So I'm just going to say frac 1 over all this mess. And then I've got meters for height. So that's where in the atmosphere it's released. And then we've got this diffusivity term. And so it's the diffusivity in the x direction times the diffusivity in the y direction, the square root of that. So, you know, unit-wise, it'll come out to the diffusivity is in square meters per second, right? That's going to be my diffusivity term. So there it is expressed in units. Looks like millimeters squared, but it's actually meters times meters squared. So I've got a meter that cancels. So I've got a square meter in the denominator. The seconds cancel. And the kilogram doesn't cancel. So I wind up with FXY as kilogram per square meter, right? And so that unit, kilogram per square meter, is mass loading, right? So that's the output of most Tephra models, is kilogram per meter squared. And it comes out of that first term, right? It comes out of the amplitude of the term. And let's look at this for a second. Okay, so Q is pretty easy to understand. That's just the mass of Tephra released in the atmosphere, right? That's how much is available. Sometimes people, there's no reason you have to think about this in terms of a mass. It's usually how people do it, but you could think of it in terms of a volume, right? So it could be cubic meters, in which case this would be cubic meters per square meter would be the output of the code. But like I said, the convention is normally we think about that in terms of kilograms. And so settling velocity is in the numerator. So the settling velocity, if the settling velocity is in meters per second, big particles, according to Walker and Wilson, big particles are going to have a higher settling velocity. Smaller particles are going to have a smaller settling velocity. So the concentration is going to depend on the settling velocity. And then that's divided by the height. So we've got a ratio here of settling velocity to height, which is sort of the soul of a lot of Tephra dispersion problems, right? So the higher the settling velocity is going to influence the amount of concentrated in a particular spot. And then I'm dividing by h, and h is the height. That works in the opposite direction. So at a given xy location, I might have less Tephra at a specific spot if h is bigger, and I'll have more Tephra at a specific spot if the settling velocity s is larger. So that ratio s divided by h is going to be important in this equation for figuring out how Tephra is going to disperse downrange of the volcanic eruption. And then these diffusion terms, diffusion is meters squared per second. So it's interesting that seconds are in there. That means that if if the settling velocity is high, then the square area is going to be larger, right? And so you can imagine that if I drop a particle from, if I hold a palm full of Tephra in my hand and I drop it, say 1 meter, that Tephra is going to spread out and make kind of a blob on the ground, roughly circular in shape. And the diffusion is how wide that blob is. And so if I release it from a greater height, go higher and higher and higher, then that little footprint of Tephra, when I release it from my hands and it floats to the ground, the footprint will be wider and wider. And similarly, if the settling velocity is smaller, takes longer for the Tephra to hit the ground, then I'm also going to get a wider footprint. So that's how these terms relate to one another. And so let's continue building this equation out a little bit. I've then got this exponential term, which I've been ignoring so far. So I'm going to say exp, and then I'm going to put a left bracket up here and a right bracket up here. I'm going to fill in what's in between. And I'm going to start just with, whoops, went too far. And I'm going to start with the simplest term. I'm going to say fraction and curly brackets in there to do my fraction. And I'm going to have y minus y naught. And that whole quantity is going to be squared. And that's going to be divided by 4 times dy. That's the diffusivity, the crosswind diffusivity, and that's going to be divided by this fraction of the release height divided by the settling velocity. And so I'm going to ignore my signs and things like that. So there's one bit that's in there. Okay, so let's define these terms. We've already defined the diffusivity, we've defined the release height, and we've defined the settling velocity of the particles. So why not, let me add that. So why not is going to be the, I think I used an O for that. It's going to be the, it's going to be the location of the volcano in the crosswind coordinate, right? And Y, which I didn't bother defining before, is the crosswind location of the measurement, where we're getting the mass loading of Tephra. Okay, so let's look at this term for a second, do the same thing. Well, you know, this is in the exponentiation, so this term should be dimensionless, right? That's Euler came up with that sort of notion. And we should say, well, y minus y naught squared. Okay, so the numerator here has units of square meters, right? And so let's look at the denominator here. In the denominator, we've got square meter per second. And then h is a height. So I need somehow to have seconds down there to have the units be dimensionless, right? Meter squared divided by meter squared. I get a meter squared out of dy. I have a meter squared in the numerator. So h is the height divided by the settling velocity, meters per second. So that second in the velocity cancels with the dy. And so this whole thing becomes dimensionless, right? What this is showing is as y gets larger and larger, that crosswind distance down from the volcano location, dy is going to govern how this thing spreads out, how the footprint of Tephra spreads out in the crosswind direction. And that's also going to depend on the release height divided by the velocity. So all these terms, dy, h, and s, that sort of group of terms, is sometimes lumped together as a sigma. And sometimes people refer to it as sigma squared because it's in square meters, right? And so it's sort of like the standard deviation of the Gaussian distribution, if you want, is in square meters, is in meters. So the variance is in square meters. And that variance really represents the diffusivity in the atmosphere, that is how turbulent the atmosphere is, or in reality, how turbulent the volcanic plume is it advex downwind. And then it's going to be a function of the release height, that is how high in the plume that particle is released, and the settling velocity, inversely proportional to the settling velocity of that particle, how long it takes for that particle to hit the ground. So if it takes a long time, if it has a very low settling velocity, you know, 1/10 of a meter per second or 0.01 meters per second or something like that, this denominator is going to become big and particles are going to spread out in a crosswind direction more and more. If h is big, it's released very high in the stratosphere or something like that, then that denominator is going to be very big and it's going to take a long time. It's going to have a very broadly spread out footprint. If h is small or the settling velocity is high, the denominator is small and the whole term becomes bigger, and the footprint is more concentrated. So that's how that works in the crosswind direction. Now let's add the dispersion in the downwind direction. And to do that, I'm going to make another fraction up here. And that's going to be minus the y direction, which I'll get into in a second. And in the numerator here, it's going to be x. That's going to be the position of my volcano, minus x naught. But I'm going to have an additional term here. I'm going to add to x naught some term related to the advection of particles in the atmosphere. So that's going to be u h divided by s. And then I'm going to close that out with a square. Probably made a mistake there. That's okay. And then in the denominator, it's going to be this whole mess, the same mess I had over here. Same diffusivity term, only now it's going to be x. Diffusivity in that direction. Let's see if I happen to get that right. It looks okay. Okay, so let's talk about this term. So now I've got x naught in addition to y naught. And x naught is the location of the volcano, not only crosswind, but downwind. And x is going to be the downwind and crosswind location of my point. And u is the only thing I got left there. And u is the wind speed. And that's my advection term. Okay, so let me run that for a minute. Okay, kind of getting this together. See how this is going here. Now, in the only thing that's different between y, oh, and I left out a minus sign here. Sorry. Okay, there we go. Okay, so the only thing going on here, it doesn't really matter dimensionally that there's minus there, but it's important because it's decaying away from the volcano. Anyway, so this whole thing looks the same, except I've added u, which is the wind speed, times the ratio of h over s, right? Which is the height divided by the settling speed. So if I have the height divided by the settling speed, I have a combined term, which is seconds, right? That's seconds. And u is in meters per second, the wind velocity in meters per second. So I wind up with meters. And that makes sense. It's got to have the same units as x naught, right? Which is a meters location. So unit-wise, that balances out. So let's look at this term UH divided by S, right? That's got to do with how long, or H over S has to do with how long it takes the particle to fall. So if I actually do a little calculation here, let me go down here and just start a calculation. Okay, so let's explore H and S. So if my settling velocity equals 1 meter per second, right? You know, I guess a meter per second must be I used to know this rule better than I know it now. I think it's something like a millimeter sized particle. Maybe I've got that wrong. Sorry if I do. Maybe 2 millimeters or something. I don't keep that stuff in my head very well anymore. And then the release height, let's say it's just a kilometer, right, in the air. So the particle is advected into the air 1 kilometer. Then h divided by s means that the fall time for the particle from its release height of 1,000 meters falling at 1 meter per second is the settling velocity divided by the release height, right? That's super, you're driving me crazy. This is too easy. Did I do that wrong? It's the, sorry, it's the release height divided by the settling velocity. Oh, it's not so easy. So that's the fall time in seconds, right? Okay, got that right. Okay, so that's the fall time in seconds. So suppose my wind velocity then is what? Let's just say 10 meters per second, right? U equals 10. Okay, then that term, let's call it the displacement of the particle, is going to be equal to U times the fall time. Totally makes sense, I think. And then print displacement. And the units of displacement should be in meters if I'm living right. Okay, and so that particle's displaced 10 kilometers downrange, right? So if I look back up here at this term that I'm using in my numerical model, this is defining UH divided by S is defining how the particle is displaced downrange during the eruption. So if the release height increases, it's displaced further. If the release height is lower, it's displaced, less distance. If the wind is blowing fast or slow, that depends on this displacement. And so technically this wind velocity, I can't even spell, this wind velocity is the horizontal wind speed, right? Because it's the velocity in the downwind direction, right? And so I'm saying that the wind is blowing at this constant rate of 10 meters per second. The particles falling through the atmosphere at a settling velocity from a release height. And that ultimately tells me the displacement downrange for that particle. Okay, so now we're in our usual spot where we can actually develop a function to describe this particular, to implement this equation. So here's our analytical solution, and it's a simple fall model for reasons we'll get into, but I'm assuming a constant settling velocity in the atmosphere. I'm assuming a constant horizontal wind speed and so on. It's a bit of a simplification, but give me a break. We're just developing a code to understand Tephra dispersion here. So I'm gonna start then by creating a function. I'll call it the simple fall model, right? And I'm gonna pass it a whole bunch of stuff. Let's worry about that in a minute. What do I need to implement this equation? Well, I need all these variables, unfortunately. So this is quite a lot of stuff that I'm gonna have to implement here. So let me just start out with some comments. I want to say S in my function is equal to the settling velocity. And I'm going to say that I'll just make it a capital Q. Oops, sorry. Comment. Capital Q is going to be equal to the eruption mass. I should, to do good coding here, I should put units in here. What else do I need? I need the release height. That's where in the atmosphere above the volcano the particle is released. I need these diffusion coefficients. In the X direction, and I need the diffusion coefficient in the Y direction. A lot of stuff. As these models get more complicated, I have basically many more parameters I've got to set in order to solve the expression, and this is sort of a an introduction to that sort of problem. Let's see, I need the volcano location in the X direction, and that's going to be in meters. I need the volcano location in the Y direction. You know, Y location, Y, and that's in meters. And I need the wind speed, right? Okay, so I need all that in my expression. I also need to know where it's going to fall. I need the coordinates for the location where the measurement is being made. So I'm going to have X and Y is measurement location. And those units are meters as well. Okay, so that's sort of giving me a clue about how I'm going to implement this thing. And I'm going to now pass variables to it. And let's just say I'm going to pass X and Y. That's my measurement location. No problem. And then I'm going to pass a sort of laundry list of variables. I'm going to pass it the settling velocity. I'm going to pass it the eruption mass, the release height, I'm just going to go diffusion X. Diffusion Y. And the volcano location X. And the volcano location Y. And I need the wind speed, right? Okay, so I think that's what I need to pass this function in order for it to actually give me an answer. Just, I can clean this up a little bit. It doesn't have to be spaced out that way, but it's kind of nice to do it. So often when I have a function that's taking a lot more variables, this is one way to deal with that list, is to put those returns in there. And I think if I run this at this point, I forgot a comma, it tells me, there you go. And I run that. Oh, geez, incomplete on line 19, which is where? I forget my line numbers. I'm forgetting on here how to turn on the line numbers. Anybody remember how to turn on the line numbers? Not sure.
I think the problem is that there's no return command put at the end, I think.
Well, maybe I need to put in the return command, right? Okay, let's say return mass loading. Okay, yeah, you were right. Thank you. Okay, but I'm bugged that I don't remember how to turn on the line numbers. It's here somewhere. I don't remember where. Okay, anyway, I've got that. Okay, and so that seems to be working okay. And what I'm going to do is develop a little bit of local nomenclature for myself. So I'm going to say here, S is equal to the settling velocity, and Q is equal to the release, or to the eruption mass, and H is equal to the release height, and let's say dx is equal to the diffusion coefficient in the X direction, And dy is the diffusion coefficient in the y direction. And let's see, let's call the volcano location x naught is the volcano location in the x direction. And y naught is the volcano location in the y direction and the crosswind direction. And then u is equal to the wind speed. Okay, so I've just developed a local nomenclature in my particular code to handle all these arguments I'm passing, right? Okay, and so what I do when I need to implement an equation that looks like this is I usually just break it up into parts. So let's do that. I'm going to say that, let's just say term 1 is going to be equal to that first term. So I'm just going to copy that down there. And I'm going to say term 2 is equal to this x term right inside the exponential. So I'm going to drop that in there. Get back to it. And I'm going to say term 3 is equal to that y term in the exponential. And the reason I do that is then I can easily say that mass loading is equal to term 1 times numpy.exp of minus term 2 minus term 3. And that should do it. Okay, and then return mass loading. And I'd like to give myself a hint that that's in kilograms per meter squared units, right? So let's see if that compiles. Okay, so that when I run that cell, I don't get an error anyway. I probably made a mistake somewhere. But this is just a little bit more elaborate function definition, and I'm passing it variables that I can read. That is, I understand what those variables are relative to this equation up here. And then inside my function, I'm just developing a local nomenclature to solve it, because otherwise these expressions get really long. Okay, and so that supposedly is going to be my simple fall model. Okay, so let's actually try to find out what the mass is going to be at some point. Okay, so I'm gonna go onto a new cell, and I'm gonna test this code, and I'm gonna test the code by creating an eruption. So my eruption, and now I'm gonna define all these variables, values. I'm gonna input parameter values for this expression to actually call that function. Okay, so I'm gonna define a set of variables to do that, and I'm going to call them ESP for eruption source parameters. And so if you read the literature on Tephra or just about any other model, we often talk about these eruption source parameters, and I'm going to define it in this way. I'm going to use keywords to define these variables. And this is going to show you why I went to all that effort before to define these words up here. So I'm going to take settling velocity, and I'm going to copy it inside this quote, and then I'm going to put a colon here, and then I'm going to put a value, 1. I don't know what it is. 1 meter per second is my settling velocity in this particular example. And I'm going to do the same thing with these other eruption source parameters. So I'm going to say that eruption mass, I'm just going to copy that. And I'm going to assign then a value to that let's just say 1e to the 6th. And I'm going to assign a value to the release height. And that's going to be, call it 1,000 meters for little plume here. I need a comma after that. And then I'm going to assign a diffusion coefficient. In the x direction, let's just say that's 300 square meters per second. And then I'm going to do the same thing in the y direction. Often in these models, we use the same diffusion coefficient in the x direction and the y direction. It doesn't necessarily have to be that way, but in general, we define it that way. Then I need to define the volcano location. And let's just make the volcano at 0, right? And I have to put my quotes in here. And then what's left? Wind speed, right? Is going to be 10. And curly bracket. So you can see how that matches the curly bracket up there. And so that is an argument list. And in my argument list, I'm using keywords. So sometimes this is called a keyword argument list. And so I'm saying there's settling velocity, mass, eruption mass. Each one of these items in my list is a keyword that makes sense to me as a volcanologist. That's very helpful. And then it's got a value. And the value is just what I'm specifying for my particular eruption, right? So what's left? Well, in order to call this function and see if it's working, I got to pass it my x and y location. So we already did that calculation that if it's got a, I think I did it up here, if it's got a settling speed of 1 meter per second and a release height of 1,000, then it should be displaced about 10,000 meters. So let's calculate x at that location. And let's do it right on the major axis of dispersion of the plume. So the crosswind distance is 0. And then I just have to call my my mass loading expression. So I want to calculate my mass loading for that point. And that's going to be equal to simple fall. And I'm going to pass it x and y. These are the variables I specified right here. And then I'm going to pass it this entire list. Okay, and I'm going to do that by saying star star, which means I'm going to pass by reference ESP for my eruption source parameter. And then I'm just going to print the mass loading. Print my mass loading. And I guess I better say that's in kilograms per meter squared, right? Okay, so if I run this, I get an error. Okay. Oh, you guys see what I did wrong? Up here somewhere, I'm going to go all the way to the top, and I'm going to insert a cell. I'm going to say import numpy as NP. Got to do that. And I'm going to plot here in a minute. So I'm going to import matplotlib.pyplot as PLT. Okay, so I'm going to run those. Better run that again, run this again. Oh, okay, I get a mass loading. Okay, is it right? I have no idea, but let's check it out. So I've input some parameters. I've said, okay, I've got particle settling. I'm releasing 1,000,000 kilograms, right, from 1 kilometer height. It's diffusing in the atmosphere. I'm downrange of the volcano, and I'm getting a value out, right? So remember up here, I predicted that 10,000 meters was going to be the displacement for me. That's cool. So if I change this to 9,000 or something like that, is the number going to go up or down? If I'm right, went down. So that means there's less tephra closer to the volcano, and it went. If I go further away, less tephra further away from the volcano. But 10,000 is the sweet spot in this particular problem because I expect there to be a maximum of tephra at that location based on this ratio up here, right? Based on this ratio of release height to settling velocity times the wind speed. So I'm messing around here with that displacement, right? UHS in this expression right here. And what you can now do some other experiments. What happens if the diffusion is higher? That diffusion coefficient is higher. Oh, the number goes down, right? Does that make sense? Well, yeah, because for a given particle fall time, there's been more diffusion, right? So that makes sense that at the maximum location, I get that value. And so that's I'm guessing not so intuitive for you at this point, this way of testing it. But what I'm doing here is just developing a very simple model of Tephra dispersion. Sorry, this one's relatively simple. I know probably you're like, what? It looks like a train wreck to me, but it is a relatively simple approach to Tephra dispersion. And then I'm getting a value at this X location. So let's experiment with this code and see if we've got what we think is happening here. So I'm going to instead do what I did last time and specify X as a set of numbers. So let's just say X is equal to NP, and I'm going to use line space here. That function LIN space, which means I'm going to put in numbers from 0 to 20,000, and I'm going to put in 1,000 numbers, right? So when you use a range, this third number is the interval between values. When you use lin space, it's the number of values along that in that set. So y is equal to 0. Okay, I'm going to still look at the crosswind direction, and I'm just going to say z is equal to simple fall. That's my number, and I'm going to say xy, and then I'm going to pass by reference my parameter list, my eruption source parameter list, and then I'm going to plt.plot x versus z. And I'm going to plt.show. Oh, there's my expression. Okay, so let me clean this up a little bit for you. I should put some labels on here. X label is that's the downwind distance in meters, right? And what's my Y label? My Y label's got to be kilograms per meter squared, right? That's my mass loading. I got to put it in a quote. And I'm going to run that. Okay, so whoop. Okay, so there's what I got. Okay, and this is a super important result to understand volcanologically. So what I'm claiming we just did is we went from the volcano at 0 out to a distance of 20 kilometers, and we look at the mass loading as a function of distance along the center line of the plume. along the major, it's called the major axis of dispersion for the plume. And what I've got then is this mass loading is centered on 10,000. That makes sense because that's where I expect the tephra to fall if its settling velocity is 1 meter per second squared, or sorry, 1 meter per second, and its release height is 1,000 meters in the air, and the wind speed is 10 meters per second, right? That's what I expect. Okay, so if I change the wind speed or I change another parameter, I should get a different shape to the curve, right? Okay, so if I go back up here and I change an ESP, let's say I change the release height to 2,000 meters, and I got to run that code, and then I got to run this code. Oh, it's displaced it out to 20 kilometers, right? That makes sense. I've doubled the height, and that displacement is now doubled. I'm going to put it back. And let's see what happens when I crank this baby up to 3,000 like I did before. I'm going to run that, and then I'm going to run my curve again, and I get a broader peak in Tephra deposition 1,000 at 10,000 meters, right? So this is essentially controlling this diffusion coefficient is part of what's controlling this the shape of this curve, right? So that's super important to understand about tephra fallout is we're using the diffusion advection equation, and basically what it's doing is displacing this tephra downrange some distance based on these parameters we stick into it. Okay. Let me take a drink of water because I'm tired of talking. Okay. Any questions about that so far? Seems okay, but that doesn't look like a tephra deposit to me. Okay, so essentially what we're doing now in the world of our physical model, what we're doing is we're dropping particles of all one settling velocity, right? 1 meter per second. So that corresponds, according to Wilson and Walker and Bonadonna, that corresponds to one kind of particle. It's got one diameter, one density, one roughness. It's falling through a very simple atmosphere, right? It's always settling at the same velocity as it goes through the atmosphere. All the particles are released from the same height at the same location and advected by the same wind speed. So if I do that, if I simplify my model, my physical world to that extent, then I get this very simple bullseye downrange for my particle. Okay, so how do I then begin to approach this a little bit more realistically? What particle? Let's start with settling velocity. So settling velocity of a particle is governed by its size primarily, its shape and roughness and that sort of thing to a certain extent, the particle's density. So settling velocity is a function of a lot of stuff. And of course, volcanologically, we know that one of the main things that happens with settling velocity is there's actually a distribution of particle sizes that are produced by the eruption. Costanza Bonadonna calls that the total grain size distribution, or total particle size distribution, if you want, of the eruption. So the total grain size distribution, TGSD, is all over the place in the tephra literature. And of course, people spend a lot of time trying to sort out, volcanologists spend a lot of time trying to sort out what the sizes of particles are. And the short story is, well, who gives a darn about what the sizes of particles are that come out of a volcano? Well, the reason we care, just about the only reason we care, is it impacts the settling velocity of the particle, right? So grain size, sorry, I'm trying to page around my page here. Grain size is not in this equation, right? Grain size doesn't appear in that equation, but some of the parameters in this equation, one of the parameters in this equation does depend on grain size, S. S is the settling velocity. And so if we want to know more realistically what an eruption looked like, we have additional information, which is about the grain size of the distribution of the eruption. And if we know the grain size distribution, maybe we know something about the settling speed. So let's look at what happens when I change the settling speed of particles. And I'm going to use the same approach I used last week. I now want to know the distribution of particles, settling velocity. Let's just stick with settling velocity. So I'm not gonna get into how big the particle is that's settling. I'm just saying there's a distribution of settling velocities. And let's just say I've got some, I'm gonna do this in a parametric way. I'm gonna say I've got a mean of underlying normal distribution. So remember, I don't know if you've come across this before or not, but if I've got a normal distribution in phi units of particle size, then I've got a log normal distribution in millimeters, right? That's one of the peculiar things we have about grain size distribution, is we use these units of phi, and that's related as power of 2, essentially 2 to the n power of to the distribution in millimeters. Okay, so let's just say this is my settling velocity distribution is going to be equal to, and I'm going to do the same thing I did last week. I'm going to say numpy random log normal, and I'm going to pass it mu, sigma, and size. All right, and let's just see if that worked. Okay, seems to be behaving for me. And I'm going to then plot a histogram for those particle settling velocities. I'm going to copy that. And I'm going to make bins here equal to 100 or something like that. And then I'm going to PLT show that. And okay, so now I've got a distribution of settling velocities, right? I'm going to put a little X label on there. That's settling velocity in meters per second. Okay, so there's my distribution of settling velocity. So remember, before I had 1, and now I have a distribution from near 0. So those would be very fine particles out to pretty fast settling velocities, 4-6 meters per second in the tail of the distribution. And so if I've got a normal distribution in phi units, I've got a log normal distribution of particle sizes. There's a relationship between particle size distribution and settling velocity. But here I've just coded it up in terms of settling velocity. I've said, okay, I got a log normal distribution of settling velocities, and this is it. You know, so what does that do to my function? Okay, so remember now, all that's changed is I've got a set of values that are associated with the settling velocity. So let's implement that in the code. So now I'm going to count through, and I'm going to solve my expression, this function, simplify. I'm going to solve it for each one of those randomly sampled settling velocities. So I'm going to say for, let's just use an index variable, I, and I'm going to step through for size. And size is the name of the variable I specified up here. That's the number, that's the total number of particle sizes or particle size / settling velocities that I'm calculating. And I'm going to put a colon there. Then inside that loop, I'm going to reassign the value of the ESP, eruption source parameter. I'm going to reassign the value of the settling velocity. So I'm going to say ESP bracket got to spell it right, settling velocity. That's going to be equal to, and then the name of my distribution up here is the settling velocity distribution. I, right? The ith value of that. So that corresponds with this. And then I'm going to say now Z, which is my accumulation, is going to be equal to simple fall. And I'm going to pass it X, Y. X and Y are the same, right? And I'm going to now pass it my keyword arguments, my ESP, or for eruption source parameter. Okay, and so that's good, but I actually have to increment this. I have to sum this over all the particles, right? So I'm going to say Z equals 0 up here, and then I'm going to say Z is plus equal to those values. So I'm actually doing a summation now across the different particle sizes because I want to get the total mass that's accumulated. And then I have to say down here, Z is equal to Z divided by size, because I've essentially now run the eruption size times. Let me go back to that in a second. I'll show you the result and then I'll explain it a little bit better. So then I'm going to do my same plot, and I'm going to plot show, and let's see if that worked. Okay, so that's now my distribution. So let me clean that up by labeling this axis. plt.xlabel is going to be downwind distance, right? In meters. And my Y label is going to be the mass loading per square meter, right? Kilograms per square meter. Okay, so what happened? Oh, geez. Whatever can go wrong will go wrong. Okay, so there's my plot. Okay, so I think this is starting to look more like a Tephra deposit. What I expect in terms of the Tephra mass loading as a function of distance downrange. And so all we're doing now is we're saying there's random, whoops, went too far. There's random variation in the settling velocity. And I'm simulating that random variation now just by running, it looks like 100,000 simulations with different settling velocities. And so instead of getting this symmetric curve, which is what I get with one settling velocity, given my log normal distribution of settling velocities, I get a skewed distribution in Tephra accumulation as I go downwind, right? So that's pretty sweet. That starts to look more like what I expect in a Tephra deposit. And by doing this, it immediately informs us of, well, volcanologically, what do we need to know about the eruption? Well, we need to know something about the settling velocity through the atmosphere. Suddenly that becomes an overarching concern. So I would go off and do a dissertation or do a study on the settling velocities of particles in my deposit. And people have done this in different ways. So Costanza, in her dissertation, developed a model for what the settling velocity is based on the particle size. It's a Stokes settling model in a atmosphere with different Reynolds numbers, different turbulence or laminar flow regimes and that sort of thing. So you can develop a mathematical model in that way. What she did after that, a few years later, was she built a huge apparatus and said, okay, essentially a wind tunnel. Okay, I'm going to determine the settling velocities of these ranges of particles. Or you can go back to, which would be incorrect to do at this point, but you could go back to Wilson and Walker and look at their empirical relationships for settling velocity in the atmosphere. But that seems to be a pretty important control on the characteristics of my eruption. And so sometimes you get people like Robert Constantinescu who are trying to look at one particular grain size of one particular density and map that distribution, because those particles should have a pretty uniform settling velocity in the atmosphere as sort of a test of this model. So if you have quartz grains in your deposit, you know, what's the change in mass loading of quartz grains as a function of distance from the volcano? That's nice because those particles seem to have a pretty uniform settling velocity in the atmosphere. So that informs things pretty well. And that's only one parameter we've looked at. What about the release heights? I could have a whole range of release heights as well, right? So instead of just varying the settling velocity, I could vary the release height. So I'm just gonna, I actually pre-wrote that code and I'm just gonna dump it in here. I'm gonna say, okay, well, let's vary release height. Instead, just to keep it similar, I'm gonna keep a very low column here, 500 to 1500 meters. And I'm gonna use a uniform random distribution. So if I plot that up, there's my distribution of release heights. So instead of the particles being released in a point source at the top of the column, they're being released essentially in a line source. And so when I do that, all of a sudden, all I have to do is change one thing in my code, right? I have to change, instead of just assigning the settling velocity, I can also assign the release height, and I can run that. Oh geez, I changed the names. Here, let me fix my code. When I was test driving this, I used a different variable. Come on. I think it's called settling distribution now. See if that works. Okay, and there's the effect of variation in release height and variation in settling velocity in my deposit. And what you notice, which is super cool, you notice that this height, when I randomly vary the height and I'm randomly varying just the particle size distribution, the curves look pretty similar, don't they? And the reason those curves look pretty similar is revealed way back up in my equation, because everywhere there's a relationship between H and S in this equation. So that fraction, if I wanted to parameterize this even further, I would simply say there's a fraction H over S, and that's what I really know. I really know the height and the settling velocity as they vary together. So if I wanted to know, say, from the deposit how high the eruption column was or something like that, I would have to first know what the settling velocities of particles were in the deposit. If I don't know that, there's no way I can determine the height of the eruption column. If I do know that, then I can translate this curve of mass loading per unit area, which I might get from mapping the deposit. I might be able to forecast what the column height was at the time of the eruption. Okay, so that's a simple fall model, and different codes like Tephra 2 or Fall 3D or some other codes, they're all good. And essentially what they do is they implement this equation in different ways, slightly more sophisticated ways than we implemented it today. So for example, there might be a relationship in the code between settling velocity and particle size. So instead of inputting a settling velocity, you input a particle size distribution. Instead of inputting a release height, you can input a range of column heights, that sort of thing. Instead of implementing a wind speed, you could input a variation in wind speed as a function of height or as a function of distance downrange from the volcano. But I wanted to show you this building block because I hope it takes the mystery out of the code a little bit. I hope it gives you an idea of how these models work. And then, so the models I'm referring to here are analytical solutions to the advection and diffusion equation. They're basically models all built around this sort of expression. You can add all kinds of complexity, you can do all kinds of interesting things. If you know how to write a Jupyter notebook, if you know how to implement this in code, then you can modify this expression as you choose to fit your problem, which is super cool. Then there's another set of codes that actually go all the way back to, I'll show you Ling Ling's paper again. They go all the way back to this expression and they solve it numerically. That is, they solve the differential equation, partial differential equation numerically. And those kinds of codes are useful if you don't want to integrate to a specific boundary condition. Like in our model, we integrated to the ground surface. Instead, if you want to know the concentration in the atmosphere because you're flying a plane through it or something like that, then you want to go back to this numerical model. And so there are sets of codes like Puff and High Split, Name, and others that are essentially meteorological codes, and they forecast where Tephra goes in the atmosphere in more of a 3D model. They're interested in the concentration of Tephra in the atmosphere as a function of time. You'll also notice that in our code, we integrated time out of this equation. Just said the eruption happens, here's where the particles wind up, right? So that's a clever solution, but it also limits what we can do. Okay, so I'm going to stop there and stop sharing the screen and ask you if you guys have any questions. Thanks for sticking out with me through that whole thing. It was a lot, but hopefully it reveals a little bit more about the nature of Tephra dispersion and how we model Tephra dispersion. Anybody got any questions? Pummeled into silence. Okay. Well, then next week, I think we're going to go on and talk about other models. I think Abani Patra and Sylvain Charbonnier are going to be back, and they're going to be talking about some numerical models for mass flows using Titan 2D and other codes. So we'll see you then. In the meantime, take care and let me know if you have any questions, okay? I'm going to stop recording. Stop.